Now, for our next talk, I would like to invite Kofi Makinwa. So you can see, Kofi actually asked me not to present his biography in very much detail, and just said he's a professor at the university, at the Technical University of Delft. But anyway, I will say a few words, just to introduce you to our audience. So Kofi holds degrees from Obafemi Awolowo University, Ile-Ife. I hope I pronounced this more or less okay. Okay, all right, I see that. And then Master of Electrical Engineering from Philips International Institute Eindhoven, and a PhD from the Delft University of Technology, Delft. In 1998, he joined Delft University of Technology, where he's currently an Anthony von Leeuwenhoek professor in the Faculty of the Electrical Engineering, Mathematics and Computer Engineering, and head of Microelectronics Department. His research interests include the design of mixed signal circuits, sensor interfaces, and smart sensors. This has resulted in 17 books, more than 300 papers, and more than 30 patents. So, Kofi, please welcome.
Okay, thank you for a nice introduction, Lina. Also, thanks for being invited to be here. And thanks to Ali for a very interesting talk. I wish somebody had been explained all of this stuff to me when I was a graduate student, an undergraduate student. It would have helped a lot. Just taking a short circuit current and looking at open voltage and getting some intuitions from that. It's brilliant. And hopefully it makes me more confident about my own talk, because I have some little RC, R resistor circuits, and so now I know you have the insights to understand how you get the answers. Okay, thank you. Okay, so a little self-introduction. So I graduated a long time ago from Obafemi Awolowo University in Nigeria. And maybe a small anecdote, none of you have ever heard about this university. And that's maybe an important anecdote. It doesn't matter where you came from, it's about what you become, right? So some of you may think, I didn't manage to get into MIT, Yonsei, KAIST, whatever. Doesn't really have to matter. In the end, as an engineer, it's about what you do, right? So that's how we measure the things. So I think my claim to fame is I repaired a lot of radios and televisions, and that's a great way of getting circuit insights. You know, you only have to touch the output of a flyback transformer once in your life to understand that 25 kV is not a very healthy situation. So you get a lot of insight. So Ali says you can't feel electrons. I beg to disagree. You can. Anyway, so I learned a lot of stuff about circuits from trying to fix. I think you learn a lot about stuff from trying to fix broken things. And that's a great way to get insight. Then I moved to the Netherlands, where I got the rest of my education, spent some time in industry, working with Philips, and then I went back into academia, where I still am. Okay, so that's me. So what am I going to talk about? I'm going to talk about ways in which we can make accurate circuits from inaccurate components. And the challenge there is, you have components from a process, or you buy components and they're not perfect, but there are many applications where we need to get something like 20-bit resolution. So if you want to make an ADC with 20-bit resolution, fundamentally what you have to do is you somehow have to divide a reference voltage into steps into 2 to the power 20 steps with accuracy. So how are you going to do this? And sometimes you have to measure very tiny signals, maybe the output of a Hall effect sensor, which is at the level of a few millivolts, and you still have to extract some dynamic range and some resolution from that. So you need to make sensors that have errors in the order of a few microvolts. So how are you going to do this? So I'm going to show you some the intuition of how you can do it, and the trick is averaging, because a lot of the time we can trade off accuracy for time. Because usually, if you want to have a lot of accuracy, you have to give yourself some time to do it. And maybe the fundamental intuition for that is that, well, there's always thermal noise. So if you want to have something super accurate, you are going to have to spend some time averaging out your thermal noise, otherwise you simply cannot measure it. And that's why in precision circuits, usually you have the time to do a measurement, and in that time you can do some averaging to also improve your accuracy. Okay, so the background, this, Ali said, well, this is a course for third-year bachelor students. I was targeting second-year bachelor students, so if it's too simple, I apologize. But anyway, so this is maybe thinking about how do you make a resistor? Yeah, we always take it for granted. We draw a little symbol, but actually you have to make them, right? And you can make them in different ways. These are all discrete component resistors, so you can put some resistive material and put some connections to it. If you want to make it a bit more precisely, you might, these are so-called film resistors, so you take a ceramic tube, you deposit some carbon on it, and then you can etch away parts of the carbon film in order to create the resistance that you want. And these are pretty well-defined resistors. And if you want to make super well-defined resistors, you could make wire-wound resistors where you wrap some a wire with a very well-defined resistivity, and then you can wrap it up around the tube and make a different lengths to get the kind of resistance that you want. But, okay, these are the manufacturing processes, but I'm mentioning them to make you understand that every time you make a resistor, it goes through some kind of process. And this process can never be perfectly reproduced. So it means that when you go to the shop or to the market and you say, give me two 10-kilo resistors, they're always going to be different, right? They're always going to be different. In fact, resistors are they're like people. No two of them are exactly the same. Certainly not at an atomic level. But even at the level at which you can measure with your multimeter, they are not the same. And depending on how much money you want to spend on them, you can get resistors with tolerances of 10%. And I say those cost millicents. And if you have lots of money, you can get resistors that have a tolerance of about 50 ppm. And then you pay tens of euros for them. And that basically means that you paid somebody else to do the choosing for you, right? So they manufactured all these resistors and they were not the same. And then somebody very carefully measured all of them. And then he gave you two that match. And that's why you're paying tens of euros. Okay. So what about on chip, right? How do we make resistors in a CMOS process? Well, typically we use some kind of diffusion process. So what we do, we take silicon and we dope it. And in order to dope it, you have to make a mask. Typically you make the mask with oxide and then you put it in an environment that's rich in your dopant, and some of it will diffuse into the silicon substrate, and then you attach some connections, and voila, you have a resistor. And you can imagine, well, in PowerPoint it looks great, but you can imagine that when you're trying to make resistors that have dimensions of a few microns on one side, this is not going to be like a super accurate process, right? Because the level of doping depends on the furnace conditions. The amount of area available for the diffusion depends on the accuracy of your mask. And typically when you make a resistor in a CMOS process, it will have about a 20% tolerance in its absolute value. 20%? How are you going to make a 20-bit ADC with 20% tolerance components? So that's the challenge, right? Some of you may be kind of shocked, the undergraduates, that is this how bad the technology is in 2023? Well, yeah. And the reason why it's this bad is because we also want it to cost nothing, right? It has to be super cheap, super reliable. And these are the trade-offs that the process guys have to work with, and this is the best they could come up with. And by the way, yeah, this is the result of 50 years of continuous development, and this is where we are. So now they turn to you, or us, as analog circuit designers. Okay, guys, here you sell 20% tolerance resistors, do it. Okay, so I will tell you how we analog circuit designers do it with 20% tolerant components. Okay, so there is one good thing, though, about IC technology. The thing is that because all of these devices are in very close proximity, they actually match pretty well. So I said, yeah, it's difficult to make two devices that are exactly the same. Well, in an IC process, you come very close to doing that, because the fact that you have two resistors that are made only a few microns apart means that you can make them they experience the same conditions in their growth or development or manufacture. So actually they can match pretty well. So although we have this 20% tolerance in their absolute values, it turns out that their matching can be much better than that. And if you do things well and you use big devices, you can achieve a mismatch in the order of 0.05%, which is not too bad. So this is the first trick. The first trick is realizing that we can make components that match in an IC process very well, but their absolute values are likely to vary quite a lot. Okay. Well, things get worse because, a lot of our circuits consist of transistors. Well, making a transistor is a lot more complex than making a resistor because it involves a lot more steps. So I was saying, yeah, you have to make a mask and then you do some diffusion and get a resistor. If you want to make a MOSFET, probably even 10, 20 years ago when we were still dealing with planar MOSFETs, it still required about 5 or 6 mask steps. So you can see the variability increasing. And today, with FinFET technology, it gets even more complex. And people are even dreaming of making single atomic layer channels, and things are going to even get much more complicated, because you can imagine, at the point at which we are counting the number of electrons in our channel, then you have actually a kind of shot noise-like stochastic variability in your transistors just by design. So as we make things smaller and smaller, the degree of mismatch necessarily increases, increasing the challenge for analog circuit designers and ensuring that we still have jobs. So that's very important. Okay, so, all right, if you want to make any kind of decent amplifier, unfortunately, you have to use a lot of transistors. And the circuit I'm showing, you recognize the bipolar transistors, is from a very famous amplifier design, at least famous if you're my age, the 5534, which was a very famous audio amplifier. And I'm looking at the faces in the room, and I can see, yes, I am slightly older than a lot of the people here, because I thought this was a very cool circuit, but okay. But the message here is that if you want to make a decent amplifier, you've got to use a lot of transistors. And all of these transistors exhibit some kind of variability. So at the end of the day, you have an amplifier, and its end-to-end gain, input-output, is going to vary quite a lot. So if you look at a data sheet of an op-amp, you will see it has a very large gain, probably about somewhere between 80 to 120 dB, which is quite a lot. But you'll see typical. That's usually what you will see. That hides the fact that the gain will spread by at least 20 dB from part to part. And with a typical op-amp, that doesn't matter in application. So who can tell me why it doesn't matter? So why are we not usually worried about the gain of an op-amp spreading? Yes? Exactly, because we're going to put it in a feedback loop, and we are basically going to kill its gain down to about 10, and then or 20 or 100, but it's something much less than 120 dB. And the power of feedback is that we actually reduce the errors by the product of the loop gain and beta, and therefore that's a pretty large number, and so the resulting error is quite low. So that's another class, the power of feedback. Maybe I need to make a circuit intuitions about that, because feedback is a very interesting idea, and the story goes that the inventor of feedback, at least the electrical engineering inventor of feedback, tried to patent it, Mr. Armstrong, back in 1900 something, and was rejected. What?
Mr. Black.
Was it Black? Okay. It was tried. Somebody applied for a patent, and it was rejected because it was a crazy idea. Why would you take an amplifier with high gain and make an amplifier with low gain as a result? This was certainly useless. Well, the patent office doesn't always get things right. I think that's the message. Anyway, so if you make a practical amplifier with lots of transistors, you're going to get lots of gain variation, but you're also going to get offset. Because if you make a differential amplifier, what you expect is that if you tie the two inputs together, then you should have zero output. Well, if you look at the complexity of this circuit, you can probably intuit that that's not likely to happen anytime soon. So there will be some offset. So how do you make a precision amplifier? And that's the meat of the talk. So let's start with the basics, right? So this is probably a circuit that all of you know. This is a simple differential amplifier and consists of 2 MOSFETs and 2 resistors. And the nice thing about this circuit, which is very old and the configuration is very old, it was used with tubes, is that it's basically symmetric. And therefore, if I tie these 2 inputs together, then I can expect that the 2 outputs will be at the same level, because everything is symmetrical, and therefore the differential output voltage is 0. So if I have a differential input voltage of 0, I get a differential output voltage of 0. And it doesn't really matter, it shouldn't really matter what the supply voltage is, because if the supply voltage goes up and down, because of symmetry, it should affect both the output nodes in exactly the same way. So again, it rejects power supply variation. It also should reject common mode variations, because if I change the level of both of the inputs in the same way, then again, due to symmetry, the output voltages, if they change, they will change in the same way, and again, the differential output voltage is 0. So this is, in principle, it looks like a bulletproof circuit, right? But it does rely on matching. And I like to show this slide that, well, this is what it looks like in cadence, and this is what it looks like when you make it. So basically, all your matching is gone. This is reality, right? So this is what happens when you tape out your chip and you get it back. This is what happened to your beautiful differential pair. It's no longer the same. And as a result of this asymmetry, because, for instance, the resistance values are not the same and MOSFETs are not exactly the same, you will get an offset and a gain error. And the offset will typically be in the order of 1 millivolt, and the gain error will typically be about 20%. Simply because of the fact that the absolute value of those resistors itself is going to spread by 20%. So what can we do? Well, first solution, well, we can do trimming. So some of you may recognize those components. You typically have them when you're trying to make something experimental. You're dealing with variability, so you make something adjustable. And I remember sometime in my career, having a demonstration for the top management of Philips, and we had a setup, very sensitive sensor setup, trying to actually use 4 strain gauges to make a touchscreen. And about 30 minutes before the top management came, I was under the table adjusting 6 potentiometers to try and trim out the offset of the 4 amplifiers and getting everything stable, and so that things would work. And then the management came, and then it works. And then the next set of management came, and of course everything was drifting because the day was getting warmer and warmer. Had to go back under the table. So basically trimming is not so much fun. It looks very, and I realized that's how you realize some things the hard way as an engineer, that it looked very good in theory, but in practice, it was very annoying, right? So there it is. The con of trimming is it doesn't correct for drift. It's a one-time adjustment. You adjust something, maybe one of these output resistors, you adjust it, and at that time t, under environmental conditions E, it works. And at every other condition, it doesn't. Okay, so that's one disadvantage. And another problem about trimming, this is how you do it these days. Now you don't do it with Kofi under the table with a screwdriver. Now you have it with maybe an array of resistors, and then you have some digital memory and an array of switches, and then you select which one of those resistors you're going to use in order to realize the resistor R1. However, what's the drawback? Well, the drawback is, first of all, you do require some kind of on-chip memory. Now, that's not always a given. If you're trying to design a simple op-amp, you might not like to have the digital process options needed to realize an on-chip memory. And you also have to make that DAC, and that DAC, or digitally controllable resistor, has a finite resolution. I mean, it doesn't have infinite resolution steps, so you cannot make infinitely small steps. So that will limit the degree to which it can be trimmed. Okay, so can be done, but it has its drawbacks. Another drawback is that in order to trim, actually, and this is a bit more subtle, in order to trim, you have to be able to measure the error. right? Because you want to trim something to 0. Well, if you want to design an amplifier with microvolts level of offset, then you begin to need rather fancy equipment in order to trim it to that level. And that's something that's also often underestimated because, yeah, you can make the circuit trimmable, but now in the manufacturing process, there has to be a precision measurement, which itself may not be so trivial. So, can we do better? Well, it turns out that we can. First of all, before I jump to that, let me just say, emphasize the pro of trimming. Trimming is conceptually very simple. And if you don't need very high degrees of accuracy, or if, for instance, you have a system and you have to put it on the bench and calibrate it, or anyway, then trimming might not be such a bad approach. Or if you are not particularly worried about drift, because, yeah, your requirements are not so high, trimming might be a good way. So trimming is still done, so I'm not, it's important, it's one of the things that should be in your tool bag, but you should also understand its limitations. Next set of solutions are to use dynamic error correction techniques. Basically, as their name implies, these are techniques that operate continuously in a dynamic fashion to reduce variability in a circuit. And they come in two flavors that I'll be talking about today. One of them is called dynamic element matching, and the other one is called chopping. So I will be explaining how those work. So let's start simply. Let's say I want to make a resistive divider with a gain of half. So how would I make it? Well, if I want to make a resistive divider with a gain of half, I just take two identical resistors and I make a resistive divider. And if I choose R1 and R2 to be exactly the same, then the output is half. But yeah, I just explained R1 and R2 are not exactly the same, so V out is not half. Okay. Well, one day somebody made the observation that, wait a second, if R1 is greater than R2, then V out should be less than V in over 2, right? I hope you can all see that. So if R1 is larger than R2, then you get your divider, the voltage goes down a bit, and it's going to be less than V in over 2, so you get a negative error. But if R1 happens to be less than R2 in this divider, then it turns out that the opposite happens and your error is positive. And then comes the flash of intuition, because as Ali said, actually, in order to invent stuff, you have to have some kind of simplified view of things. Otherwise, things get way too complex. I've never met, actually, anybody who said, I invented something based on a mathematical description of a circuit. Usually, they would say something like, as Ali said, I have a voltage follower, and its output impedance was too large. So I thought, maybe I can use gain. I can reduce it by applying some gain somewhere. And then the person now starts looking for topologies in which you can apply gain, and then we end up with a flipped voltage follower. It's not that the guy did a lot of mathematical analysis and then he said, oh, if I make this configuration, then it works. No, that's not the way it works. So you need some kind of simplified view of how things work. And this is the simplified view of this resistive divider, that if R1 is too large, the error will be the output will be too low, and if it's too small, the error will be too large. Okay, so then comes the idea, oh, suppose we flip things around. Suppose we make two circuits. So we just switch the position of R1 in the circuit. And then we get an error that is sometimes it's too large and sometimes it's too low. And if we take the average of them, then we should get a good result. And it turns out, and you can do, and now you need a little bit of mathematics because it's not evident that you can appreciate intuitively that the error will somehow be reduced, because in one condition the error is too large, the other condition the error is too low, and if you take the average it should be smaller. But it's a bit surprising to find out when you do the math, the error is actually 0. Which leads to the interesting fact that if I take any two resistors and I put them in a resistive divider and I swap them like this, I can make a perfect divide by 2. That's kind of amazing. So it means that I can make a perfect divide by 2 with any 2 resistors. Am I missing something? Is there a catch somewhere? Yeah? Time, well, you need time. But as we will see, you have the issue of the ripple, right? Because, well, I'll come to that. But in principle, this is true. So if I have a perfect averager, and I make this configuration, and I take the average of the output voltages, I get an output voltage that's exactly half. So it's extremely powerful, because it means that with resistors with 20% or even lots of mismatch, I can still make a perfect resistor divider, which is a bit of a, which is very reassuring, because yeah, this is how you get precision from inaccurate components. Okay, so so how do you actually make this? Well, you would make it with some switches, right? So you have two, you will take 2 resistors, and you have some switches associated with them. And the idea of these switches is that you can use them to swap effectively the position of the resistors in the circuit. And so you need switches, and you also need to average. So you need a low-pass filter of some kind. And that low-pass filter can be in the digital domain, it can be in the analog domain, but you just need something that you can average. It's also important, if you look at the output voltage of this guy, it is going to look something like this. So sometimes you're around Vin over 2, you're going to get a voltage that sometimes it's too high, sometimes it's too low, sometimes it's too high, and sometimes it's too low. And now you can see in the time domain, and that's why drawing timing diagrams is also a very important part of circuit design. In fact, drawing pictures is a very important part of gaining intuition. And that's what Ali showed with his glass of water example. The ability to draw a picture of something is often the first step towards getting intuition. So when students tell me, I don't understand how something works, and the first thing I ask them is, can you draw a picture? And many times they can't draw a picture of the situation. I say, you see, that's the beginning of the problem. So I help them to draw a picture, because we are very visual. That's how our brains work. We see things, and then we actually see them. So when I show this picture, and I look at the voltage, you can immediately, I hope, see that the duty cycle, the time in which I spend in these 2 states, is very important. Because if I spend too much time in one state and only a short time, then the average is not going to be Vin over 2. You see that from this drawing. But if I just told it to you without this drawing, then it becomes a bit abstract. So the duty cycle has to be 50%, and you go, oh, okay. But when you see the picture, you can feel it for yourself. Anyway, returning to the question I asked before, why is it that if I have a big difference between R1 and R2, there's a problem? Well, because the amount of ripple that I will get, the amplitude of this square wave just becomes bigger and bigger. Indeed, it has a perfect average of Vin over 2, but I get this big ripple, and now my low-pass filter or my averager has to deal with that. And since no low-pass filter is perfect, if this square wave has a huge amplitude, then some of that huge amplitude will leak into my output, and maybe I might not like that. So the DC value is correct, but on top of that, there's some AC fluctuation, which I probably don't want, because I wanted to divide by 2. I didn't want to divide by 2 with freebies like AC ripple. But this is the basic idea. It's very simple. It's called dynamic element matching. Okay, can we take it a step further? Yes, because I've talked about the divide by 2, but if you only could make divide by 2s, that would be kind of boring. It turns out that you can make a divide by n. Oh, that's nice. So I can make one resistor, and I can make a resistor R, n minus 1. And how do I make that? Well, I need to make n resistors, and basically I need to take these n so-called identical resistors, and I need to interchange them in the circuit. So I need to ensure, and this is the key point, that each of these resistors spends the same amount of time in different positions in my divider. And if I do that, I can show And with Ali's circuit intuitions, it's probably a piece of cake to show that if I look at the average voltage of all the n different states in which this circuit can be, I can show that the output voltage on average is exactly equal to V in divided by N. Again, irrespective of the initial value of those resistors. So it's kind of wonderful. So with dynamic element matching, I can take N mismatched resistors and make a perfect divide by N. And why is this important? Because this is the fundamental circuit that you might like to use if you want to make a precision A to D converter. You need a voltage reference that has accurate steps. And okay, you cannot make them accurate in a static fashion at one moment in time, but in a dynamic fashion, and taking n cycles in order to do it, you can. Okay, so this is the final generalized concept. I can make an M to N ratio. So basically, this is my divider network, and I can make all the steps that I need for a precision A to D converter. Okay, so this is the first concept, dynamic element matching. What about looking at things a little bit in more detail? Because Ali has said, okay, yeah, you have some intuition and we know how it works, but what are the downside? What's the downside? Well, the downside is this ripple that I mentioned before. And one way of looking at dynamic element matching is that there's a gain I want to have. In this case, where I started was half, but there's a little bit of error. And what I do with dynamic element matching is that I toggle the polarity of that error. So I make that error sometimes positive, sometimes negative, so that when I take the average with my low-pass filter, it cancels. So that's the model of dynamic element matching. And then if I look at the output spectrum then at this point, what you will see is I have my DC value, which is nice, but I'm now going to get all kinds of harmonics, because basically what I'm doing is I'm multiplying my error with a square wave. And this is where, yeah, things start to get a little bit complicated, because it means that I'm creating, I get a DC, everything is perfect, but at other frequencies, I'm getting some ripple. And this ripple, I should remove it, and therefore I need a low-pass filter. And that's in red, shown in the frequency domain. And that low-pass filter has to be well designed if I want to ensure that these ripple components don't become annoying. Also, another thing that I have to watch about is for intermodulation. Because you can imagine that if my input signal happens to be at exactly the same frequency as this square wave, bad things are going to happen. Because if I multiply two signals with the same frequency, then I get components back at DC, which is exactly where I don't want them. So that gives me a limitation. So from this picture, again, from this picture, no maths so far, you know, look, no maths. From this picture, we can see that the bandwidth of the input signal has to be restricted to the DEM frequency, this frequency at which I'm rotating these elements, divided by 2. Now, of course, now if you really want to know with a particular filter how much intermodulation will I have, now you can open up your mathematical tool bag and you can really do the analysis, or you can go to Cadence and do some simulations. Okay, so here's another example of dynamic element matching to show it another way of using it. We rather than making an attenuation, which is kind of, yeah, okay, people don't really like attenuation, we like gains, right? Gains are better than attenuations. So how can you use this idea to make an amplifier with a gain of 2? Well, you put a dynamic element matched divider to make your 1 over beta, and use it to make it very accurate, and now you see the same trick being used again. But the interesting thing is, in this non-inverting topology, I get this signal, and you may think, oh, okay, it works perfectly, I get exactly 2 times V in. I just wanted to show you that in this particular example, the power of your mathematics is that if you take the average of this, you don't get exactly 2. And why is this? Well, it has to do with the topology that I'm using, but there's an error. There's a residual error which is proportional to R divided by R. R is the mismatch divided by big R, the nominal value, squared. And you may be thinking, well, Kofi has sold us a dummy because now there's this topology and it's not working so well. Well, it's important to realize that this parameter, this error, is squared, which is pretty powerful because it means that if you had started out with some 0.1% tolerance resistors, when you square that, you get 1 ppm. So the fact that there's still a small residual error is not really a practical problem. With them, we can reduce, let's say, mismatch of 0.1% to the ppm level, and this is the only practical way I know to get this kind of precision on the chip. Any questions so far? No? Okay, you're great students. All right, so now we jump to the other way in which we can use the power of averaging, and that's called chopping. So chopper amplifiers are used where you need very low offset. And we're going to use the same trick again. In this case, the error is offset, and we are going to, by using this topology, you will see that we are able to persuade the offset to appear with a positive polarity and with a negative polarity. And again, if you take the average, then the offset disappears. So how do we perform the magic? So let's study this block diagram in a bit more detail. So here you have some modulators, and 2 modulators, and you have your amplifier. And I've tried to show using superposition, another one of those handy things. So I've separated the activity of the signal of the circuit into what it does with the signal, expressed in black, and what happens to the offset, expressed in red. So if we imagine that we put a DC input into this setup, and we modulate this DC signal, we get this square wave in black over here. The square wave will get amplified, and we get a larger square wave, and then we demodulate it again with exactly the same kind of modulator, and then this square wave is converted into a DC voltage. This DC voltage goes through the low-pass filter and appears at output. So you can see that this amplifier, even though it looks very complex, does what you would expect from an amplifier. It takes a DC signal and makes a larger DC signal. But now let's see what happens to the offset. The offset in red is introduced here. It's introduced after the first modulator. So it's not modulated. It gets amplified, and now it sees the output modulator and it gets changed into a square wave. And this square wave goes into the low-pass filter and disappears. So nice. So somehow we have waved our magic wand, and we have turned our offset, which is DC, and we have changed it into a higher frequency AC signal where we can filter it out. Again, the power of averaging. The low-pass filter is doing the averaging, and it's allowing us, and the modulator is doing the shifting. So the modulator shifts our offset up to some higher frequency, and our low-pass filter averages it out. So this is the concept. How do we make this perfect modulator? It turns out that in CMOS, it's very easy to make this perfect modulator. We just use 4 switches. That's nice, because with 4 switches, we can effectively change the polarity of a signal. And by changing the polarity of the signal, we are effectively multiplying it by +1 or -1, which is exactly what you want, what you need in order to make a square wave modulator. And the nice thing about this is that it's extremely accurate, because there are very few error sources in this. There are still some, because of course the switches will have some resistance. Resistance will cause thermal noise. They will take some time to close. They have some charge injection, but all of these are advanced topics. To a very good degree of approximation, you can make very nice switches in CMOS, and therefore you can make very accurate modulators. All right, so the last complexity, looking at things in the frequency domain, because when you look at things in the time domain, you can gain one kind of intuition, and when you look at things in the frequency domain, you can gain another kind of intuition, which is interesting. So I always encourage people to think about, when you're trying to develop some intuition about the circuit concept, think about it in the time domain, and if that doesn't work, think about it in the frequency domain, because some things are easier to understand in the frequency domain in the time domain. In principle, they are interchangeable, But as all of you know, in some cases, the Fourier analysis that you need to get to the same result in the frequency domain is really not worth the trouble, and sometimes does not provide you any intuition at all. Whereas looking at it in the time domain may help quite a lot. So for instance, one question that I'm asked very often is, okay, so is there any limit on the chopping frequency? And the relationship between the chopping frequency and the input frequency? And I say no. And they say, well, but what about intermodulation and stuff? Then I say, well, just consider what happens if you take two polarities reversing switches and you put them in series. So basically, they both change at the same time. And I put an input signal. What happens? Answer, nothing. Because they change polarity, +1 times +1 is +1, -1 times -1 is still +1. Or if you draw the circuit with the switches, you can see that nothing happens. So to first order, of course, this is only true to first order, I can chop at any frequency I like, and nothing will happen to my input signal, because I am chopping and unchopping perfectly. Now, in practice, of course, this is not the case, because the amplifier has delay, and then if you look at the delay of the amplifier, then you can see some bad things happen as you increase your frequency. But for the intuition, looking at it that simply in the time domain explains a lot of things instantly. People say, oh yeah, that's clear. Then you can move on. If you try and do it in the frequency domain, that becomes very painful, because then you have to look at the spectrum of the square wave modulated waveform, and then you have to apply the demodulator, and then you have to do all the maths, and you get eventually, after 3 pages, you get to the same result, but there is no intuition coming from there. Okay, so coming back to the frequency domain, let's look at what happens, what a chopper amplifier does to a signal in the frequency domain. Well, I put in the signal, and the signal gets modulated. So basically the signal, which I've drawn here at DC, gets up modulated to harmonics of my modulation frequency. So these are the harmonics, the first, third, and the fifth, because that's the way a square wave works. And here you can see the nice picture, because you see the offset and the low frequency 1/f noise stays at DC. Then I take all of this, I amplify it, and I pass it to my demodulator. And what my demodulator will do, it returns my information to DC. But now my offset and noise get up modulated to the harmonics of the chopping frequency. And if I make this low pass filter in this way, so that its cutoff frequency is somewhere below the chopping frequency, you can see that it's possible for me to remove the up modulated offset and some of the up modulated 1/f noise. So this is now where the intuition is coming, that chopping can also help to get rid of low frequency noise, which is also a problem in precision circuits. And the final result will look like this. Another intuition that you can gain from this is that, well, I have had to put a low pass filter. And that's true actually of all of these techniques, dynamic element matching and chopping. I have to average. And in averaging, I'm going to lose some bandwidth. So there is no free lunch, except the ones that John provides. There's no free lunch in circuit design usually. If you win something, you're going to lose something somewhere. So one of the titles of my favorite book titles is called "Beware the Naked Man Who Offers You His Shirt." It's brilliant, right? Telling you there is some kind of free lunch. No, there's no free lunch. These people that meet you in the street, we have this offer for you. Yeah, if you had this offer for me, you would have used it and become a millionaire. The fact you're offering it to me means there's probably the catch somewhere. I just have to find it. But anyway, so last thing I want to talk about is residual offset, because no technique is perfect. So if I do chopping, I've shown you all the waveforms, and you can see that if I look at the up-modulated offset, the duty cycle really has to be exactly 50%. Otherwise, I'm going to have some residual offset. This average value of this red signal is not going to be 0. It's going to be somewhere else. Kind of exactly what happens with dynamic element matching. And just to give you a numerical example, which you can consider as a little homework exercise, if I have this amount of initial offset, I'm chopping at 50 kilohertz, and I have a nanosecond of clock skew, which is quite reasonable, already that will give me a residual offset of 1 microvolt. So I encourage you to try it all at home. And that brings me to my last slide, summarizing everything. Basically, what I hope you can now understand is that by virtue of the fact that they need to be manufactured, all components exhibit some kind of variability. Your first line of defense is trimming. You can adjust components, but you have to realize that this will not correct for drift. It requires an on-chip memory and extra measurement equipment. And by using dynamic element matching, we can make ratios. So not absolute values, we can make ratios with ppm levels of accuracy. And we can also get rid of drift. And with chopping, we can achieve microvolt levels of offset and also low drift. And the catch, the cost of this lunch is that you need an averaging low-pass filter. And this averaging low-pass filter will limit your bandwidth. So the use of this dynamic error correction techniques involves a trade-off between bandwidth and precision. So that was my last slide. So thank you for listening.
Now we have time for discussion, so how many questions?
Yeah, so my question is in regards to the delay on the op-amp, on the chopping. You mentioned that like the frequency can't be too high, otherwise it would mess things up, right, on the chopping. So my question is, since you're switching or modulating the signal that's entering the op-amp, right? So does that delay not matter? Like, I'm sorry, my question is a bit all over the place, but what I'm trying to say is it really like that ignorable if your frequency is lower? Because at least in my mind, the varying of the entry of the op-amp would still like really mess the way the signal comes out, because the image you have on the other slide makes the output be really nice and rectangular, but in my mind doesn't make any sense for it to come out like that.
So you are looking for the non-idealities of chopping. So I've explained the principle. So this is the first step, right? The first step is this is how it works. Now, the rest, now come the second order and third order effects. First of all, if I use a very high, so fundamental to chopping, maybe I can use this picture, is that this amplifier, what is it amplifying? What is its main job? Its main job is to amplify the up-modulated signal. So that means it has to have gain at that frequency, right? So if I decide to chop at gigahertz, suddenly I have a problem, because then I need an amplifier that has gain at gigahertz. So in this sense, what chopping does is it kind of takes away some of the advantage of this amplifier, because all amplifiers, at least the ones I know, have a much higher DC gain than AC gain. So that's an issue, right? So you have to, that's the reason why you like to generally chop at the lowest possible frequency, because most amplifiers have a sort of low pass response. So if the lower the frequency at which you chop, the more effective gain you can get from your amplifier. That's one. The other point is you're restricted though, because if you chop at, you also want to chop at a sufficiently high frequency that your 1/f noise is moved out of your band, because you can see from this picture that if I chop at a lower and lower frequency, eventually some of my 1/f noise, that sloping dotted line, will merge with my input signal. And I wouldn't want that, right? Because the reason I'm chopping is I want to get rid of the offset and the 1/f or flicker noise. So I have to chop at a certain sufficiently high frequency to get rid of that noise. So those are two, let's say, constraints that you have with chopping. I hope that helps. Yeah, okay. I think people want to go for lunch. The free lunch.
Can I just ask one, maybe it's a naive question? Okay, so Okay, so when we look at this technique, right, so there's an amplifier, modulator, LVF, and those must be also well-designed circuits, right? And we have transistors when we have an implementation. So, and then maybe if you go to a more advanced technological nodes, there's going to be mismatches and kind of variations. So, and we talk about, like we talk here about like quite a lot of complexity in the overall design, right? And you also may think about like the area that the circuit will take up and also maybe power consumption as well. So taking all of that into account, like, would you kind of, give maybe one example where you would still apply this because it's an important application and you still apply this to some particular classes of signals or maybe like some application, and where you would not bother to do this because maybe there is something else, or maybe, that's already over complex technique?
Okay, so where would I not use these techniques?
Yeah, I tend to ask negative questions.
Well, okay. Where I would not use these techniques are questions in applications that are speed limited. Because like as I've explained, you do need a certain amount of time to do the averaging. So in RF circuits, for instance, where you have to operate at gigahertz or even multi-gigahertz frequencies, you don't have the time to do averaging. In which case, trimming is all you got. Right? But fortunately, when you're dealing with those high frequencies, maybe flicker noise is not so much of a problem. If you're designing oscillators, it still is, but okay. So in very high frequency applications, you don't have the time to do averaging. And therefore, these techniques might be rather difficult to apply. Yeah? Okay.
Any more questions from the audience? Yes.
Maybe I just had one observation. I was thinking about intuition when you said that it doesn't work when you put it around the feedback loop exactly, the math doesn't work. And I think it's because when you have two values that are going up by plus delta and minus delta, the average will be 0. But if you invert them, 1 over x and 1 over x plus minus delta and minus delta doesn't add up to 0. Just because of that inversion that you put around the
Yeah, that's a good way of looking at it. Indeed, the 1 over x kinds of spoils things. But okay, if some questions don't come to mind, never fear. I'm still going to be around for the next 3 days. So Ali has already made me to be the wandering, walking target. So in case you lack the intuition, come and talk to me. No, go and talk to Ali. Ali is the guy who writes the articles on circuit intuition. So if you want the circuit intuition, go and harass him. Thank you very much for listening.
All right, so it's now a lunch break, and we will be back after lunch. So
1:30.
1:30.